We are closing the doors, and Jeremiah here is going to start off and start talking about using symmetries to secure large legacy software. So everybody, welcome Jeremiah tonight.
Thanks, everyone. I'm going to talk on this topic of using software symmetries. So I'm going to start off with two math problems to kind of get our minds thinking in the right direction. Then I'm going to give some background about NSoft, where I work at. We're up in Ames, and about some DARPA projects we've worked on to give you some background of some idea of where we're coming from. Discuss the challenge with large legacy software, and then this idea of software symmetries. So this is a really old math problem. So in the 1900s, or leading up to the 1900s, there was a lot of advancements in mathematics, and there was a lot of excitement about the power of logic and reasoning. And this famous mathematician, David Hilbert, thought that anything that could be formally specified through logic and reasoning could be fully understood, right? And he thought the limits of knowledge there were no limits of knowledge. Unfortunately for him, in 1931, Kurt Gödel proved that the number of things you can formally prove, is a subset of the things that are formally specified. And so computer programs, so later that's what Turing looked at Gödel's result, kind of lie at the border of that. We can prove some things about some computer programs, but we can't prove everything we want to know about any computer program. So sort of a computer science version of that question is, does a problem have a computable answer? So here's a problem that's formally specified. And so it's a question, does this problem have a computable answer? So if you have all the base 10 numbers less than 10 to the 100,000, composed of only digits 0 or 1, how many are divisible by 7? Right, so for example, 1,001 is divisible by 7, right? Comes to 143. And there's such numbers. Tons of these numbers exist. How many are there? Right, so can we compute an answer to this? So you give this to most computer science students, they'll say, well, I'm going to do a loop, because I can easily enumerate base 10 numbers with zeros and ones and test each one for divisibility by 7. The problem with that is, even if I have a machine that at 5 gigahertz can test one of these at each cycle, the heat death of the universe will happen much sooner than me getting an answer to this question. All right, so there's problems like this. This is formally specified. Can we compute an answer? So that can be your homework for tonight. You can send me an email if you figure it out. Okay, so some background about us. So NSoft is a spinoff from a lab at ISU. We were founded in 2002, and our customers are all the major automotive, aerospace, and defense companies worldwide. So most of them are actually the Japanese automotive companies. So that's about half of what we do. And the other half of what we do is we do cybersecurity research for DARPA. We've had 3 multi-million-dollar projects so far, 2 of them as a research team and 1 as a system evaluator. And so the way kind of this happened is we started working with avionics companies, and they have processes to ensure safety properties. And we proposed to DARPA, can we use some of their techniques to ensure cybersecurity properties? And that's how we came from this kind of complex machine world to the cybersecurity world. And so I don't know if everybody knows how this DARPA thing works, so I thought I'd give some background. How many people have heard of DARPA before? Everybody here? All right. So maybe this is superfluous, but so DARPA was founded in 1958 after Sputnik was launched. The Department of Defense didn't like being surprised by this, because if Russia can put an object in space, surely it can put an object in North America, like a nuke or something. So we wanted to create surprise and anticipate surprise instead of being surprised. And the way DARPA is organized is there's offices. So there's like a robotics office, a biology office, et cetera. My programs have been under the Information Innovation Office, and they're organized. They have 2 arms. One is program analysis, and the other one is big data. And so I work under the program analysis side. And typically those I2 programs, they range in funding from $50 to $120 million. They typically have about 6 research teams, so blue teams. They typically have 2 adversarial teams. And they have 1 white team, which is the evaluation lead, which sort of sets up the challenges between the blue teams and the red teams. And sometimes there'll be other teams, like a control team or an integration team or a platform provider. So my area is program analysis, and one question is, why is program analysis hard? So fundamentally, it's hard because of branches. right? So we can see here, if we're trying to analyze this program, see the diamonds are the branch points, right? I need to keep some state about the program as I'm analyzing it. Each time I get to a branch, my state duplicates, right? And then I get to another branch, my state duplicates again. And here I have a loop, right? Every time I go to that loop, the state multiplies. So this is some statistics from the Linux kernel. So we can see in the Linux kernel there's 16,000 functions with over 50 control flow nodes. But these branch points are what make programs very difficult to analyze. They have a lot of varied behaviors, but that's what makes software so powerful, right? That's why we use software. Okay. So this is a little bit more background on how program analysis is done or what the challenge is. So these states explode, and I need to keep track of all these details about the program to try to prove some property about it. But that's very computationally expensive. So the fight in program analysis is always between sort of precision and speed. Because what many techniques do is they abstract the program, sort of they make a simplified version of the program. And so it's easier to prove properties of that simplified version. But then I have to argue, does that property apply to the real program? So that's why most bug checkers are really horrible, because they find these bugs that don't actually exist. On the other hand, I can increase the precision. But when I increase the precision, it's almost like running the program exhaustively through all the different inputs. And we don't have enough computing power to do that. So currently, most of the state-of-the-art techniques are they're called SEGAR techniques. So this is called counterexample guided abstract refinement. And so what they do is they try to start at a sort of an abstract space. And if the technique feels confident that it found a real answer, then it says, I'm done for that case. If not, then it makes a sort of a backs off from the abstraction, makes something more concrete, keeps going for a while, and so on and so forth. And this will actually produce correct results if you have an unbounded amount of computing resources. But we don't have an unbounded amount of computing resources. So sort of in this research field, the big success was in 2007. They had a 12,000-line code. And they were able to do 34% of the cases, prove whatever property correctly. For the other 66%, they ran out of time. But this is the state-of-the-art sort of hung around there for quite a while. Okay, so I just want to give you some idea of what the problem is of program analysis. Now I'll give you some idea of the DARPA programs that we've worked on. So this was a joint project with Iowa State University, and this one from 2012 to 2015. And so the attack scenario that DARPA had in mind is they thought the Department of Defense infrastructure was very heavily secured. So it's much easier for an attacker to hack into the source code repository of one of the contractors. And then when the application was deployed at the Department of Defense, then something would trigger the malware. Right? And so they wanted to know, is there some efficient way to audit these applications? And when they looked at the commercial space, most commercial malware is financially motivated. They found that a sophisticated state actor is not, whatever coding patterns or whatever techniques were there were not catching things that an advanced state actor could do. So they wanted some technology to do that auditing. So this is one of the examples of one of the early challenge apps they gave us. What this does is that it corrupts your GPS location, but only within a certain GPS square. Right, and so at the time, DARPA always likes to pick an application area. So this program, the application area was Android devices or Android applications. And there were some cool examples of this. For example, they had soldiers doing urban patrols. The problem is soldiers are told to randomize their patrol, but they're human, right? So they kind of have a pattern to how they patrol, and then they would get ambushed. So they said we should have an app with mapping that generates a truly random patrol that we still cover the space so that we need to patrol over a period of a week, right? But you could have a situation where somebody hacks that application, puts something bad in there, and it'll, when you're within a certain location, maybe when the night when there's a full moon, we'll send the patrol to a particular spot and be ambushed. So in any case, this particular GPS location, this code segmenter here, it's in Afghanistan. So if you were testing this app in Iowa, it would behave perfectly. So the challenge is sort of, how do you look for a needle in a haystack when you don't know what the needle looks like, right? And it could be a very obscure trigger, so testing isn't going to find it. So you have to come with some hypothesis, of how this could be. So this was one of the programs we worked on, and we built some tools to help with this. The second program is the STACK program. So they're looking for space and time vulnerabilities. So there, what DARPA was looking is, in the future, all communications are going to be encrypted. So with the fully encrypted communications, what can we exfiltrate? By only observing the response times and the size of the packets. And there the application area was basically web applications. Okay. And the third program here is the CASE program. So what the CASE program is looking at is they sort of say we want to be like post-cybersecurity. They want to talk about something called cyber resilience. So it said, let's assume that the vehicle will be hacked during a mission. How can we be resilient to the attack? Can we still complete the mission during an attack? Or can we back off gracefully, right? For example, maybe we can't complete the mission. Maybe it was a surveillance mission and the camera was compromised. But can we still fly home so the vehicle isn't captured by the enemy, right? Or maybe we can't fly back home, but maybe we can make sure that we can guarantee that all the data is removed before the vehicle crashes. And so in this program, we're actually the system evaluator. We're not one of the research teams. So we get to sort of grill the performers and find out the ins and outs of their methods and advise the program manager on how the performers are doing. So any questions so far? Okay. Okay, so moving on to large legacy software, right? So this is an era of large legacy software. So for example, this is the diagram of all the devices on a CAN bus on a low-end sedan, right? And Bill Mazzara from Fiat Chrysler rightly calls cars data centers on wheels. It's not a computer on wheels, it's a data center on wheel. The Android stack is over 10 million lines of code, right? We have huge COBOL code still working in a lot of financial institutions. And so we often view large legacy software as kind of a, it's a bad thing, right? But actually, software can't become large and legacy unless it's doing a useful job for a long period of time, right? And this software has outlived hardware, but it'll probably outlive many people. I remember going to Wells Fargo, this was in the early 2000s, and there was this gentleman, Wayne. We were helping to do some modernization of the COBOL code, right? And you could see the comments in the code, right? 1970, Wayne did this change. 1982, Wayne did this change, right? 1993, Wayne, right? And Wayne was there, right? Wayne, I think, was over 80 years old, and I don't know how much they were paying him to stick around. But anyway, so this is a slide a lot of DARPA presentations like to use. So they noted alarmingly that when they surveyed their own, some of the government systems for where the vulnerabilities was, a third of them were actually in the security software, right? And they're not recommending you to use the security software. Maybe there'd be a lot more problems, right? But, this software itself is becoming large legacy software. Okay. And the problem is only getting worse. So this is a slide of the size of different avionics systems code. And we see from 1970 to 2020, this is a logarithmic scale. It's just increasing, right? It's getting out of hand. And what are we going to do? Okay. Maybe this is more of a little a fun aside. So this was in collaboration with ISU, and one of the grad students ran this experiment. He got an old CVE, and he decided to get, he found every antivirus, like bug checker, vulnerability thing he could find. He found 55 of them, and he found that only 30 of them could identify this. I think by the time he did this, the CVE was like 4 years old or something, right? And then he said, let me do something simple. Let me just change the class names and methods. And 2 of them couldn't identify it anymore. He obfuscated the strings. Now, only 16 could find it. And eventually, he just used a simple XOR packer, right? Like simplest encryption in the world. And now none of them could find it, right? So we have a difficult situation, right? And so this is a slide from Don Kaufman, the former I2O director. He says the fundamental problem is we have an asymmetry, right? Our software gets bigger and bigger and bigger. It's expensive, and a hacker with a few hundred lines of code can bring it down. So this is a big challenge. Um, so some of the efforts at DARPA and I guess at other places have been, it's like, well, this really sucks. This legacy software really stinks. We need to start with a clean slate. And we have some success with writing systems from scratch. So the SCL full microkernel is 9,000 lines of code. We can prove many properties about it. It was built from the ground up to be provable. But that took about over 5 years to a decade to develop, right? And the real-world systems we have to secure are tens of millions of lines. They have a lot of very useful functionality. That's why they're large legacy systems. So we can't really rewrite things, right? We have to live with our code. So what do we do? So our group came up with a hypothesis. Our hypothesis is actually that we shouldn't disparage the large legacy software. We think actually the larger and older a piece of software is, the easier it should be to devise some method to prove some interesting property about it. And the reason is because we think there should be some underlying symmetry to the software. It should emerge because as the software gets old, certain things, certain bad things about it, or certain irregularities will naturally go away. For example, Bosch makes components for most of the automotive companies, right? So if you get an active, like an ABS brake module from Bosch, that code has been put in hundreds of variants of that brake. It's been driven for billions of miles in real and virtual test tracks before it's ever deployed. And that software has been written in trillions of miles by actual customers. So there's some kind of bugs that just don't exist in that software. And when you build a program analysis tool to analyze that software, you can make certain useful assumptions that help you simplify the analysis problem. So those methods, like we talked about the cigar method, the idea there is let's make a general purpose software analyzer that can be used by many pieces of software. Unfortunately, because of the halting problem, it's difficult to do that. So instead the idea here is let's look at some particular software, a particular class of software, see what internal symmetries it has and try to exploit that. And the larger and older a software is, we think the more likely it is something like that could be exploited in it. So some questions arise from this idea. So one is, how quickly could we mine a piece of software to discover its particular symmetries? How quickly could we build tools to exploit the symmetries? Is there a taxonomy to these symmetries, right? And can we maybe someday have this awesome tools that will automatically figure out the right symmetry and pick the right technique for that piece of software? Okay. I want to present a couple of case studies of this. So this was an early success we had in our group, sort of before we codified this idea as a symmetry. So in the mid-90s, the US government said, we don't want to keep giving federal labs these large amounts of equipment funds to go buy foreign supercomputers. We want them to buy American supercomputers. And the problem was that the foreign supercomputers were shared memory supercomputers. The American ones were distributed memory supercomputers. So the software wouldn't run without doing some porting of some kind. And the problem about automatic parallelization or automatic porting of these parallel codes is it's an NP-hard problem in its generality. So we were looking at this problem, and what we noticed is if you looked at the bulk of the codes running in these supercomputers, these were physicists running physics simulations, or it was weather models, or different kind of mechanical simulations. They all use something called finite difference or finite element method. So we said, instead of trying to, and there were a lot of groups, this was a big financial problem. A lot of groups were trying to make this automatic parallelization tools. We thought we should just build a tool that can only parallelize these finite difference or finite element method codes, instead of trying to solve this big general problem, right? And so we built such a tool, and the big success was this MM5 weather modeling code. So MM5 is sort of a kind of continent scale weather modeling code. And a lot of research groups use it, so there's a lot of sister codes. So you take the MM5 and you put your own math in it, another group does it. So a group at Oregon National Labs parallelized their MM5. It took them 3 man-years to do it. And using our tool, it only took 2 person-weeks to do it. Right, so that's a 75x speed up because we said there's a symmetry here, right? FEM and FDM methods walk the matrices in a particular way. There's a particular strategy to distribute them in the supercomputer. And the way we decided to architect this was, we had the legacy Fortran code. We had a diagnostic tool that told us are those symmetries actually present in that code? Are the assumptions that we need in order to make a correct analysis and a correct parallelization present? And then we would proceed and do the parallelization. Okay. So 2 other case studies here. So the second one is it's from the Moscow Institute of Physics and Technology. So they were looking at this BLAST tool that I was talking about before. And they thought it should do a lot better. And they wanted to verify properties of Linux drivers. And so what they noticed is some of the failures were because of the underlying method, right, the mathematics of it. But some of the failures were just, this was not dealing well with some idiosyncrasies of the Linux kernel. So, it's kind of the symmetry idea, but kind of halfway, right? BLAST was not designed from the ground up for this, but let's try to adapt it. And they were able to reduce the failure rate by half, and they were able to handle 12.4 million lines of large Linux kernel, right? So this is a fantastic result, right? We went from looking at 12,000 lines to looking at 12 million lines, and the failure rate was halved, and the thing took 61 hours to run. So this is a fantastic result. So then our group started looking into this, and the problem we wanted to, go ahead.
What did they do to achieve those results to increase the efficiency and the number of lines of code?
A lot of it had to,
Pretty impressive.
yes.
I mean, like, what's the secret sauce?
I think a lot of it had to do, a significant part of it had to do with the Linux build. The Linux build is very complicated. And so they found that people were just kind of throwing the driver code at it without properly communicating the flags. That was one piece of it. There were some other changes internally, which I don't have my head fully wrapped around. But yeah. So, yeah, maybe I can look it up offline too. I feel I haven't given you a satisfactory answer.
Yeah, no, it's okay. I don't want to hold you up. I mean, that is really impressive.
Yeah, that is really impressive, yeah. So we kind of were inspired by that, but so our group, this case 33, we kind of took it as a challenge, right? We were like, well, they're still failing on 33% of the cases, and by God, it's taken them 61 hours. So we built a tool from the ground up to try to exploit these symmetries inside the Linux kernel. And so we actually worked with the Moscow team to get an apples-to-apples comparison. We wanted to have the same version of Linux with the same build flags on the same hardware. And so we're able to get, for the lock and unlock cases, for that verification problem, we were able to verify 99.4 of the cases. So nearly 100%, and it only took 3.4 hours. So that was an 18.6 speed up, because our tool was, from the ground up, built with this idea of what is special about the Linux kernel that we can exploit to do a correct analysis. Okay. So I just want to give you like sort of a glimpse of one of the things that we did to do that. So we defined this concept called a projected control flow graph. So most of the verification tools, when they work, they say simulating the program, right? Going through all these steps, going through the branches, keeping all that state, it's very expensive. So we want to prove as many properties as we can when we're doing that analysis. So what we decided to do is look at it from a different point of view. Could we reduce some of the state that we need to keep track of if we only prove one property at a time? And so the idea here is that you can define some events that are relevant to the property you want to prove. And it's not coming out here because of the projector, right? But we have 2 events here. There's E1 up there and E2 over here, right? So, suppose that those 2 spots really were the only thing you needed to look at for the particular property you're trying to prove. So what we see here is that no matter how the program goes, you're always going to hit E1 up here, right? And there's all these branches here, and you'd have to keep a lot of state. But no matter which one you take, you'll eventually hit E2. So with respect to E1 and E2, this simplified control flow graph is equivalent, right? So you can think of some ideas that, there's a set E of events, all the events of interest for your particular property. And you can have some set T of all the possible traces, right? For all inputs of the program, all the traces of the program, but that only contain the event E. So the idea is to define a simplified control flow graph that will produce all the same traces with respect to the set of events E as the original program. And so it turns out these are much smaller. So here in the Linux kernel, for example, after we do this compaction, the number of control flow graphs with over 50 nodes go down from 16,000 to 6, right? The ones with 31 to 50 nodes go down to 109. So this greatly simplifies the computations you need to do for the analysis. So, we can define the events for locking and unlocking or for memory allocation, and then we prove one property at a time. And some of what makes this possible is because the Linux kernel, the way they use locking and unlocking is very disciplined, right? They try to define, they're not passing their locks on the heap and through parameters and in complex data structures, because otherwise the human beings maintaining the code wouldn't be able to, properly think about the locks and, make sure that they did their job correctly. So this is the idea of the emerging symmetries. Maybe somebody did something crazy with locks at some point in Linux kernel. Maybe Linus rejected it offhand, but that bad code wouldn't have survived all these years in the kernel. So that's sort of the pattern, right? Look for how the software is architected, exploit that. Right, so this has some implications, right? So that's a great result. We got 99.4% accuracy for that property. But the problem is, there's a significant human expense in coming up with the right concepts, right? Like the BLAST tool, you can download it, you can throw it at any code that you have, and it'll find some bugs, and then some it'll fail, and that wasn't much work, right? But for us to get this kind of accuracy, we had to have a team of grad students and PhDs looking at this code very carefully for a long period of time. So it's expensive to come up with these symmetries. But on the other hand, the symmetry-based approaches can produce extremely high accuracy. That just can't be achieved with generic methods. So what I see is that there's two approaches to make the symmetry thing cost-effective. When the short term is, you only apply them in high payoff situations. If it's not a high payoff situation, it's very expensive. In the long term, though, I think we need to put in more research into reducing the cost of discovering symmetries, right? So tools for understanding the software for mining symmetries, and reduce the cost of building tools that can exploit the symmetries. And so we can, coming back to our hypothesis, right? The larger and older a piece of software is, the more likely some symmetries exist, right? And the software is large in legacy because it does something valuable, right? So large legacy systems are the place where we can have this high payoff, right? Maybe it is worth to, if we have a software that we really care about, like the Linux kernel, to go ahead and build these tools that analyze it. The other thing is, it's a good thing that we're living in an age of these large legacy softwares, right? Maybe 40 years ago, when computer science was young, we didn't know what symmetries would emerge. Now we have lots and lots of these systems, right? So we should be studying them and see what common patterns programmers have used to make them survive for these long periods of time, and how we can exploit those to make accurate analyses of them. So this is my last slide, and I don't know if it's overly complicated, but I kind of try to bring various things together here. So when you're proving, so this again is what we started off with our first math problem, right? The things that are formally provable are a subset of things formally specified, and computer programs lie in that boundary. And so when we say we want to prove some property of a program, right? So we want to prove, for example, memory safety. What we're actually doing is we're proving a bunch of little subproblems, right? So in a lock and unlock, we're proving each instance of a lock, right? And so sort of a way to restate the hypothesis is the larger and older a piece of software is, the more instances of subproblems that can be proven should exist in that software, right? And how do we know a subproblem X is provable? Well, we need some method that finds an answer, right? So in the work that the Moscow folks did with the BLAST program, they found that 67% of the cases were formally provable, right? We ran them through, and we know they existed here. The cases that were left over, we don't know. Maybe they are formally provable. Maybe the software is architected in a way that no analysis can prove they're right or wrong. But what we do is we improve the method, right? So we attack the problem, and we were able to dispense with 99.4% of the cases, right? So we know they were in the blue there. So the way you go about this research is you start with some known methods. You see which ones can be properly proved. And then you study the leftovers, and you see, is there something about the parts that weren't addressed that I can exploit to build an analysis to address them specifically? And you kind of go through this iteration. Now, in this case, where you only have a few cases left, maybe what you should actually do is just modify the software so that they get rid of some patterns in the code that make the thing difficult to prove. So that's the presentation. I think I timed this for about 40 minutes, so I'm a little early, so. Do we have any questions from the audience?
So back to the symmetries. Is that just state functions that reside within all common applications? Is that what you're using as a symmetry?
I'm using the term somewhat generally. I want to say like there's some common pattern or practice that's used within the software. So in the one about the supercomputers, what it had to do is that all the matrices were either 1 or 2 dimensional, and the code would walk the matrices in a certain order. It wouldn't randomly access them. So that meant when I broke the matrices apart, I could use I could make certain assumptions about where the data needed to be on each computer, right? In the Linux case, it was that the locking and unlocking, the locking objects didn't go through complex data flow. They weren't passed around all over the place. Like in automotive code, if I want to look at one of the properties for automotive and avionics code is that all loops need to be bounded. And so I need to prove that. So because of that, I know that either the loop will have a constant or it will come from a global. So I don't have to do a complex simulation of the heap when I make an analysis. So it's really somewhat specific to the application. But what we notice is when an application has lived for a long time, like it tends to not do all, there's still crazy things in there, but the number of crazy things isn't as large, and a lot of things are fairly regular. So what we've really done in our group, for these DARPA projects is we noticed we were sort of building similar infrastructure each time we build an analysis tool. So we built a platform that made it easier for us to build yet another analysis tool. So we have a platform called Atlas, and that we reuse in all our DARPA projects and in the private tools we do for our commercial customers. But yeah.
Thank you.
Yeah, welcome. Any other questions?
I'll go
No, go for it.
So we have like a big monolithic COBOL application where I work at.
Yeah.
Any good pointers for kind of going through there and executing kind of what you did for these other applications with that to kind of help ensure the security of the application?
It's hard to say to have a specific pointer. I don't know. I could talk to you offline about that. Yeah, that would be cool. Yeah. Yeah, so I guess I think it's too restricted to say it. I'm assuming they make logical decisions. I think that it's more like certain types of stupid decisions get burnt out over time. Right, so if, like in the automotive case, all kinds of dumb things, like for example, in the automotive code, you don't see a lot of pointer arithmetic, right? I looked at, it was transmission code for a large truck, right? They had this code, it was 50,000 lines that only had like 12 cases of pointer arithmetic, and they were all fairly disciplined. Because I imagine whoever used pointer arithmetic, right, developers do dumb things. The testing guys caught it and removed it. So it's more over maybe it's survival of the fittest in terms of the code. Doesn't mean it's bug-free, but it just means there's pressure to remove certain types of bugs.
Kind of like reading a book again and again and again.
Exactly.
If you're proofing a book multiple times, you're going to make changes that are going to fix it.
Exactly. That's a very good analogy. Yeah. So any other questions? All right, well, thank you very much for having me. I really enjoyed this opportunity to share this with you.